All right, let's jump right in. For decades, astronomers have been staring up at the night sky, slowly piecing together this magnificent puzzle of how planets are born, how they live, and how they eventually die. We've built these massive telescopes, run complex computer simulations, and developed incredibly rigorous scientific models. And honestly, for a long time, we were pretty confident we had the cosmos figured out. But recently, we've stumbled onto something that completely shatters our best scientific models. We have found planets that, according to our very own laws of astrophysics, simply should not exist. Just to give you a sense of scale here, over the last few decades, we have confirmed over 6,000 exoplanets out there in the universe. We've cataloged rocky worlds, gas giants, ice worlds, you name it. And with every single discovery, we genuinely thought we were reinforcing our understanding of how planets formed. We had our categories, we had our rules, and everything seemed to fit neatly right into the little boxes we built.
But that brings us to the core of this explainer. We've found over 6,000 planets. We thought we understood the rules. These three prove we don't. Today I'm taking you on a cosmic detective story. We're going to look at three entirely real, meticulously documented worlds that absolutely break physics as we know it. And just to be totally clear, this isn't science fiction. Every single impossible thing we're about to discuss is a confirmed scientific reality.
Part 1. The Planet Formation Rulebook. Okay, to truly appreciate how these new planets break the rules, we first need to establish exactly what those rules are. Astronomers generally rely on two baseline expectations to explain how giant planets come to be. First up, we have core accretion. Think of this as a slow, gradual buildup of dust, pebbles, and boulders into massive planetary cores, which then sweep up all the surrounding gas to become giants like Jupiter. Then, our second rule is disk instability. This is a much faster, violently rapid process where a massive cool disk of gas and dust becomes unstable and directly collapses into fragments that form planets. For years, pretty much every planet we found could be explained by one of these two processes. Until now.
Case 1. The zombie planet, Hala.
Let's start with a world astronomers affectionately call Hala. It's a Jupiter-sized gas giant located about 520 light-years away, orbiting a massive red giant star named Baktu. Now, Hala's impossibility isn't about how it was born, but about how it somehow managed to cheat death. You see, stars like Baktu, and eventually our own sun, exhaust their core hydrogen and swell up massively into red giants. Observations show that Baktu absolutely went through this phase, inflating out to 1.5 times Hala's current orbital distance, meaning the star expanded far beyond the planet. Hala should have been completely engulfed, incinerated, and torn apart by the star's fiery expansion. Yet, astronomers looked through their telescopes and found Hala sitting right there, completely intact, on a stable, nearly circular orbit.
So, the crucial question we have to ask ourselves is, how on Earth, or rather, how in the universe, did Hala survive a fiery cosmic death? A planet simply cannot survive inside a star. For a while, the leading theory was that Baktu was originally a binary star system, basically two stars orbiting each other, kind of like the fictional planet Tatooine. The theory went that these two stars merged, and this insanely violent collision halted the red giant's expansion just in time, sparing Hala from being swallowed. It was a neat, elegant solution.
But science is never that simple, is it? A massive study published in Nature in June 2023, followed by a really detailed 2024 study by Chen and their team, completely unraveled that neat little solution. They recalculated Baktu's age and found it's only 1.9 to 3.5 billion years old. For the binary merger theory to actually work, the star would need to be way older, around 9 billion years. So this new age makes the merger theory highly unlikely. Now, there is a lingering alternative hypothesis that a current mass estimate of 1.7 solar masses might mean a slightly larger orbital distance somehow saved it, but honestly, this remains completely unresolved. So we're right back to square one. Hala survived an impossible engulfment, and today nobody fully knows how. It is a true zombie planet.
Case 2. The Impossible Giant, TOI 6894b.
If our first case defies death, this second one defies its very birth. Let's escalate things and look at a system located 241 light-years away in the Leo constellation. Notice the severe mismatch here. On one side, you have the host star, TOI 6894. It's a tiny red dwarf with only 21% the mass of our Sun. It is incredibly small. On the other side, you have the planet, TOI 6894b. It is a massive, Saturn-sized gas giant that whips around its tiny star every 3.37 days. In fact, this planet's diameter is 40% the size of its entire host star. This is literally the highest planet-to-star size ratio we have ever seen. And here's why this matters so much. Core accretion, our leading model, requires a massive disk of dust and gas to build a giant planetary core. But a tiny red dwarf simply does not have enough raw material in its initial disk to build a core big enough to create a Saturn-sized planet. The math just does not add up. Even our backup theory, disk instability, completely struggles to explain how a planet of this exact size could form here. It has too much mass for one theory and not enough for the other.
MIT astrophysicist Emily Pass really hit the nail on the head when she said, quote, "Theorists who model planet formation are not able to create planets like TOI 6894b, end quote. I mean, it's incredibly refreshing to hear scientists be this plain-spoken about what we don't know. This Saturn-sized planet breaks every current formation model we have, period.
Finding this planet was no easy feat either. Astronomers had to scan through 91,000 stars just to spot it, officially detailing it in Nature Astronomy in June 2025. But we definitely aren't giving up. The James Webb Space Telescope is officially scheduled to study this impossible giant's atmosphere. By checking its metallicity and searching for rare chemical signatures like methane or ammonia, we might just find the missing puzzle piece that explains how this world came into being.
Now I want to bring our momentum to a sudden halt with this exact quote. What the heck is this? This wasn't said by some casual observer. This was the genuine collective reaction from top astronomers when they pointed the most powerful telescope ever built at our third and final planet.
Case 3. The Unprecedented Alien, PSR J2322-2650b.
Brace yourself, because Case 3 is by far the most bizarre, otherworldly, and completely unprecedented planet we've found so far. Located 750 light-years away in the Sculptor constellation, we have PSR J2322-2650b. And the absolutely crucial point here is its host star, a black widow pulsar. I want you to imagine a dead neutron star packing the entire mass of our Sun into a sphere roughly the size of a single city on Earth. It spins insanely fast, blasting out intense gamma radiation every few milliseconds. It gets the name Black Widow because its radioactive wind literally cannibalizes and strips away any companion stars unlucky enough to be nearby. And incredibly, against all logic, a Jupiter-mass planet is surviving right next to this monster. The physical traits here are cinematic. It completes a full orbit in just 7.8 hours. It is hovering at a distance that is just 1% of the gap between the Earth and our Sun. The pulsar's gravity is so intense it has literally stretched the planet into the shape of a lemon, and because it's tidally locked, one side takes the brunt of the intense radiation while the night side is shrouded in this mysterious dark soot.
But guys, it gets weirder. When the James Webb Space Telescope scanned its atmosphere, the data made scientists' jaws drop. They found an atmosphere dominated by helium and pure molecular carbon, specifically C3 and C2 molecules. There's absolutely zero nitrogen and zero oxygen. We have literally never seen an exoplanet with this composition. Normally, carbon bonds with oxygen or nitrogen, but here, it's just pure carbon. It rules out every single known formation mechanism in astrophysics. We don't know if this planet formed normally, or if it's the stripped-down dead core of a star that the pulsar cannibalized, a mystery documented in the Astrophysical Journal Letters in December 2025. Because there is just so much pure carbon, scientists believe the intense pressure deep inside the planet actually crushes it. The carbon crystallizes, and you literally have diamonds raining downward toward the planet's core. It is a world of pure, extreme physics that we barely even have the math to comprehend.
Rewriting the cosmic rules.
So, what do these impossible planets mean for the future of science? Why does any of this matter to us? Well, look at the composition of our galaxy. Red dwarfs, those tiny stars that shouldn't be able to host giant planets like our second case, TOI 6894b, they actually make up 75% of all the stars in our entire galaxy. If our models say giant planets can't form around them, but we've just proved they absolutely can, that means there could be billions of undiscovered giant planets out there, silently orbiting in the dark, totally defying our expectations. The huge takeaway I really want you to grasp from this explainer is that scientific uncertainty is a beautiful thing. These impossible planets aren't glitches or errors in our data. They are invitations to think bigger. Being honest about what we don't know is exactly what drives science forward. The universe is under no obligation to follow our models. Our models must adapt to follow the universe. As we wrap up, I want to leave you with this provocative thought to ponder the next time you look up at the night sky. We didn't find planets that broke the rules.
We found planets that proved we never knew the rules to begin with. What else is hiding out there in the cosmos, waiting to rewrite our textbooks? Stay curious, keep exploring, and I'll catch you in the next explainer.